Good afternoon. Um, Welcome to this tech deep dive session on from sidecars to the kernel. I'm Hitesh, staff engineer at Sharechat, and this essentially is a migration story led by our team where we, migrated our in-house service mesh from, sidecar-based service mesh to an eBPF-based service mesh, and this the focus of this talk is going to be around Kubernetes networking, service meshes, and kernel level data planes on GKE. And we will be going through how it works and yeah. So a typical Kubernetes native Envoy sidecar based service mesh works something like this, that you have a bunch of pods in your Kubernetes environment, and then every that has an application container that runs the business logic. And along with each of those containers, you have Envoy sidecar, which runs as a proxy, and there's a control plane. In that control plane, the job for that control plane is to configure those Envoy sidecars with endpoints and routing configurations, and there's a thin layer. So for all the packets which are coming in or going out of your application container, uh, all those packets are hijacked by a thin layer called IP tables, right? Yeah, thin layer called IP tables right here. And what the job of IP tables is to basically capture all those packets, send them to Envoy sidecar, and then Envoy sidecar takes the decision that how those packets should be routed to whichever destination they are supposed to end up at. And in that IP tables, for the low latency system that your app business logic is trying to access, these could be databases, caches, could be Kafka, Scylla, and other sort of in general low latency systems, right? In IP tables, the decision is made that if the packet is supposed to get to these kind of systems, they should not be sent to Envoy sidecar, because having a sidecar adds a fixed cost of 2 to 5 ms latency on top of whatever, compare it to an environment where there's no service mesh, there's no sidecar, right? And because there's a sidecar, you have to allocate resources to that particular container, and that really depends on what is the volume of traffic being handled by a particular pod, and that really depends on the kind of services that we run, that we scale up and scale down. And we had close to 10,000 of these sidecars running, and we are currently running more than that right now. So what broke at scale? So let's understand the scale first. So we have 300 plus microservices in our ecosystem, and most of these services, close to 70% of them, are sort of orchestrating services, which are like thin orchestrators on top of these low latency services systems. They get the data from all these systems, and then they stitch them together and then send the response back to the client. And we had close to 10,000 Envoy sidecar running in our system, close to 1.5 million RPS handled by these sidecars, and about 100 IP table rules. Now, most of these services are, because they are stitching services, what happens is like the network IO is a major work that needs to be done by these services, and the network layer that run on top of which these pods and services run. Then again, Envoy adds flat 2 to 5 ms latency on top of these sort of stitching services, most of our workloads. And on because what happens is when we talk about low latency systems that we have here, with sidecar, if a service's P99 is close to 20 ms, 25 to 5 to 10, adding 5 to 10 ms on top of it, it's like adding 25 to 50% latency on top of existing systems, which will really be not a wise thing to do, right? Now, like I said before, we had bypass rules, but just to make sure that we are not breach the SLAs. But eventually, what happened was at scale things went wrong. Now, additionally, from the cost perspective, close to 5% and close to 5 to 8% of our compute was already running just the mesh sidecars. And let's talk about the sidecar tax. Why it in the bypass, which was made from the IP tables did not save us. So routing traditional sidecar-based service mesh works something like this: that you have, let's just say, pod A communicating to pod B. Packets of pod A will originate from there, and then they'll be evaluated by the IP tables, because IP tables live at the lower layer of your Linux stack. Every single packet will be evaluated by IP tables. It will be copied to the sidecar user space, and then because the network configuration is shared between the containers, Envoy, when actually making and forwarding those packets to the actual destination, IP tables will be evaluated again. So there's a 2x cost of having IP tables within your system. And so essentially we can segregate the tax into three categories. First is the architectural tax, where having an Envoy sidecar itself adds latency, and there's a fixed per pod cost. Then there is the decision tax, that is there at the IP tables layer, where packets are evaluated sequentially twice. That adds 5 to 10 ms per hop. Then is the bypass tax. The return rules themselves, when evaluated for every single packet, tend to add certain latency on top. Each exemption is a linear walk, and it's a linear walk, and it's not a hash lookup, which will be done in a constant time. So the packet, when trying to actually leave the IP tables, it gets slowed down because of itself. So the mitigation of having bypass rules, itself became the bottleneck for these low latency systems. So this is example of a config dump of IP tables, where you have the list of return statements. That if you look at top, this is how we define a packet. Packet has source information and the destination information. The destination port, which could be any of these, which is like Scylla, Redis, or anything. If the packet destination port matches any of these, it's supposed to jump out of this. So these are the statements that guarantee that behavior happens. And after hundreds of such rules within our system, as we onboarded so many services, right? We have last rule at the top, which says that if the packet does not match any of these rules, just send it to a port called 15001, which is a standard port in our in-house service mesh, on which the Envoy listener socket is there, right? So that is how that is what the sidecar tax is all about. So we wanted to solve a couple of problems here, and not having sidecar, making IP tables much faster. So we evaluated a couple of things that are available. So the first thing we explored was the Cilium service mesh, because we are predominantly on GKE. GKE ships with a Cilium service mesh, which is built in at the CNI layer. But that particular Cilium is a lockdown version, and it does not support running proper service mesh kind of architecture on top of it. Then we evaluated Istio Ambient. It removes the sidecar, but the problem is it uses something, it uses IP tables. It uses IP tables, but we completely wanted to avoid, given the behavior and the scale that we have observed in our own system. And we wanted to get rid of IP tables completely. So before we started tinkering about what ideas there are, what new things we can explore, let's define the problem statement very clearly. We want to remove the 2 times evaluation of IP tables for every single packet in the system, and the fixed per pod cost. We wanted the interception to be transparent, meaning that the client and the server do not see that the proxy is in between. And that also technically means that no application changes will be required. Application can very well run as they were running before, during the migration and after the migration. No compromise on observability. We want to make sure whatever we are observing now, it should continue. We should getting all those metrics as is, plus there should not be any performance penalty. And then the migration should not be a big bang cutover. It should be gradual. And we wanted to have step-by-step migration, that we onboard some services first, observe what is going on, and then scale it out. So we asked this question: what if the sidecar tax could be made near zero, and we keep the every single service mesh feature? And this is where eBPF, it stands for Extended Berkeley Packet Filter, comes into picture. But what is eBPF? It technically is a way to run custom programs into the kernel and you know do some sort of manipulation at several layers in the Linux kernel. It is very similar to running JavaScript in the browser. And when you talk about similarity, it is like when a user clicks a button, what should happen? You run your custom logic right there, right? Within the browser. So you write some eBPF code, which is like any kind of packet manipulation at the network layer, or could be socket manipulation at the socket layer within the Linux kernel in C or Rust. You compile it, and then you load your program into the kernel at runtime. And because kernel is a very sensitive sort of piece in the entire Linux infrastructure, what happens is it needs to verify your program for any, infinite loops or invalid memory access and, some variables not being defined and so on and so forth. Then it compiles using just-in-time compiler your what is called bytecode into native machine code, and that gives it absolutely like 10x performance. And then you attach your program into a kernel event, because everything is event driven. Packet arriving, packet leaving, socket connection being created or getting destroyed, right? Those kind of events you basically attach your program to, and then you observe. eBPF provides a way to have persistent data during runtime. And what happens is like you write, you do connection tracking or you do telemetry recording from your eBPF program, you write into those maps, which can be read or written from user space. Let's just say you have a controller, which we'll talk about later, but this is where eBPF maps come into picture. So this is the user space where you write and compile. The kernel space handles verification, compilation again, and then attachment, and then you can observe from the user space. So how we thought about using eBPF in our system. Here we tried 4 approaches. One of them worked. So this is a very high level overview of a Linux kernel stack. You have processes, all different layers. These are sort of the abstraction layers, and every packet has to go through each of these layers. So initially, the most obvious and intuitive way is to start as close to the hardware, which is device and drivers. You run a program at the hardware layer, which is running TCP at the XDP layer, it's called, Express Data Path. When you run your program, you get the max performance. But the thing is, because it's very early in the stack, if you look at packet arriving or packet leaving, not enough information is present to work with in terms of manipulating the routing at this layer. Then we evaluated eBPF at TC, or traffic control, or TCX is sort of the newer version of TC, right? And here we could manipulate packet coming in, going out, and we did have sufficient information about how do you want to manipulate. Does this layer provide also all the sufficient data structures and everything else to manipulate as well as observe what is happening at that particular layer? So this was one of our first candidate. The second one is like running eBPF at the net filter layer. This is equivalent of pushing IP tables, which we do not want. And then information at the SOCOPS layer or the C groups layer is 2 cores. We wanted to packet level steering, not socket level steering, right? So multiple hook points we evaluated, and things are event driven. Now, how does the architecture look like at the eBPF traffic control layer? So this was our previous sidecar based architecture. Now we have something like a daemon set, and eBPF program runs at the vicinity of the application pod or the application container, because sidecar is not there anymore in the new architecture. And eBPF program does the handles by IPT in eBPF program. There is that logic, that decision is made in the eBPF program whether the packet should be sent to Envoy or should it be skipped. Envoy runs as a daemon set, 1 shared instance per node. Previously we had 10,000 sidecars. Now it's reduced to the number of Kubernetes nodes that we run in the system. That's a 5x reduction we saw when we moved and scaled this to production. That's a significant improvement. Only the packets that need L7, L4 treatment are sent to Envoy using eBPF, and the Envoy pod on the same node receives those packets from the pod running on the same node with like the application pods. And all the other packets bypass Envoy, and the checking, that decision whether to send or not is now executed in O1 time. And yeah, this is sort of that snippet of code from our eBPF program where you just call a function is port excluded, which checks that the argument that you see here is the packet's destination port. We check that if that port is present in our map of excluded ports, in O1 time we get the get true or false, and if it is true, then we return out of our program and then let the packet being processed. It should be processed, naturally, means like no proxying should happen, and send it to Envoy sidecar. So packet flow summary of how interception happens. So your application container, now eBPF program sits in vicinity of your application container. So the interception happens, and the logic also sits here, whether or not to send it to Envoy. Then the kernel space redirect happens to the Envoy socket running on the running in the pod on the same node as the application pod. So that is very important to understand. Then Envoy gathers those packets, forms a request at the L7 or L4 layer, makes the request, then Envoy needs to proxy that to the original destination where the packet was actually destined to. It does that, gets the response back, then it mirrors the forward path. Means the packet came from here to here, then it was delivered here, Envoy got a response back, then exactly the same path in the reverse order will be followed. It should be followed, otherwise, who knows where the packet goes. Yeah. Now, I just talked about very briefly about the controller. How do we manage the eBPF program's lifecycle given the pod that we are loading it into and unloading it from is itself ephemeral? So we need a controller to manage, because naturally eBPF programs are not, by default present in the kernel. So there's a controller that we have called Dante daemon set that also runs as a daemon set, by the way, to watch the pod events in the cluster. And those pods, if they have the annotations about whether we want to set eBPF routing on those pods, it monitors for that. It gets that pod information, writes the pod information into the metadata into the eBPF maps, and then attaches the eBPF programs on the pod's networking interface, and then it reconciles them continuously, because if there's a drift, then that drift needs to be made 0. And then that reconciliation, alongside that, Dante also reads those maps for telemetry data and exports the metrics as in Prometheus format. And then once the pod is deleted, or due to, could be any reason, could be scale down, or could be a spot interruption, or whatever the case may be, it's supposed to detach those eBPF programs as well. So let's talk about, before we deep dive into this, let's talk about Kubernetes node level networking. So pod-to-pod communication essentially happens via network interface pair in GKE and in Kubernetes as well if you're running Cilium. And it looks something like this, that you have a node, Kubernetes node, you have this pod. There's a network interface pair. You have H0 network interface within the pod itself, which in its own network namespace. And these are ephemeral network interface created by Cilium. Then this one-on-one is mapped to the pod's networking interface. So packet coming from here is naturally ends up on this particular networking interface. And then what happens is Cilium does the heavy lifting of identifying based on the packet destination, that if I am trying to reach a different pod on the same node, it will make sure that the packet ends up here by identifying the MAC address of this particular network interface on the same node. So packet coming here, CNI does the heavy lifting of identifying the MAC address of this particular destination. It will jump from here to here, and then it will, because this is again the the network interface pair, right? Once a packet ends up here, it will end up on the destination pod. And then the destination pod, if it wants to send a packet back to the caller or the client pod on the same node, it will just traverse the path exactly backwards. So how does a TCP connection get established? You can send a SYN type of packet to your destination. It ends up here. The packet jumps from here to here using CNI, and then it ends up here. Then a reverse packet is sent of type SYN ACK. Then the server, then the client, sorry, again sends a NAC type of packet that, hey, I accepted your SYNAC packet. Now the TCP connection is established. Now the application, not the two client and the servers can communicate with each other by sending the data packets. So we have three custom eBPF programs: app outbound, waypoint outbound, and waypoint inbound. And because Cilium also runs at, configures eBPF, the newer data plane v2 version in the GKE, it has its own SIL from container and SIL to container. Let's understand what these things, what does these programs do. So I've just zoomed in into the view that we saw from the last slide, where you have the workload pod here, and you have the net. This is the host in which this particular pod is running. So what happens is when you do a telnet, for example, from this to this destination, or whatever destination, I'm sorry, whatever destination, let's just say you make a call to another service, the packet will end up, if let's follow this blue path, the packet will end up on SIL from container eBPF program, which is default. And kind of like these programs are layered on top of it. Means first this will execute, then our program will execute. Because Cilium attaches the program at the very early stage in the pod initialization phase, we cannot like do that override. And that's okay. That does not matter in our case. We just have our app outbound program run after the SIL from container, and then that app outbound program runs the decision that whether it should be sent to the network interface of the Envoy pod on the same node in the host, or should it be sent to its natural destination, which is there, which is defined by the destination information on the packet itself, right? And if it needs to be sent to Envoy, again we do the heavy lifting instead of Cilium now, because we need to identify the MAC address of this particular network interface and then send the packet to here. And once the packet ends up here, the natural path is to go up to a SIL2 container eBPF program and then end up on the network interface on the pod of the Envoy pod here. And then when an Envoy wants to send a packet back, exactly the same path in the reverse order is followed. The packet ends up on SIL from container program, waypoint outbound program is executed, which basically helps us identify the MAC address of the client or the caller pod. Once the packet ends up here, natural path is to go to SIL2 container, and then it ends up on the client pod, right? Now we have established the forward path and the reverse path. Now, if the packets are able to flow symmetrically, across a path, what could happen is we can establish a TCP connection, and once that is established, the client and the server can talk to each other and exchange data packets. Yeah, so that is the entire flow. So you can see like 1, 2, 3, 4, 5 are the packet request packets to Envoy. Response packets flow is like 11, 12, 13, and 14, which we just discussed. What we measured. So we thought of kernel data plane as like just another production system, and we're supposed to measure it like one. We cannot say like if it is lower in the kernel, let's not measure it, let's not do this, because it's a very sensitive layer in the kernel Linux architecture. If something breaks, it could take the entire Kubernetes node down. So the observability contract that we had when we were deploying this. So we are supposed to measure service to service latencies. There should be significant improvement because there's no sidecar. Then there's no IP tables as well. CPU and memory per pod, because Envoy, instead of now being run as sidecars, it runs as as daemon sets on every single Kubernetes node. Packets per second throughput at both eBPF hooks level and the node local Envoy level. Because we are using data stores, the eBPF maps within the kernel, we want to make sure that they have sufficient they're not filled completely. Otherwise, things could go, bad, because we do connection level tracking there, and a lot of other telemetry data is there. We could miss any kind of telemetry data, which could be important in terms of debugging the issue later. Then the reconciliation time, pod coming in, coming up, going down, all this information, and then henceforth the decision to load or unload eBPF programs, that needs to be reconciled in a fixed, that should also have a strict SLA. Then the rollback time, the loading and unloading of eBPF program in the Linux kernel is atomic, and we continuously exercise this in production. So we validated the hypothesis by having an A/B type of rollout, where we were running services, in an A/B format, one on sidecar based service mesh, the other one without it and purely on eBPF. And this is what we noticed. We saw 50 to 40% improvement in the P99 latencies on the IO heavy services. These are network IO heavy services, which comprise most of our services in production. Then there was about 2500 plus CPU cores saved, which is like 63% of our service mesh footprint. About 1 terabyte of memory saved because of these sidecars, now gone. We now handle close to 1 million packets per second by on an average one single pod. And eBPF actually runs on evaluates these packets. The program evaluates these packets per CPU. So now the evaluation is parallelized as well. Opt-in rollouts, like I said, we do not want a big bang cutover. We will want to do it gradually. So we use annotation-based decision making in terms of whether a pod should be eBPF loaded or not. Then the reconciliation state, any pod goes down or goes into non-running state. Those information needs to be there in the kernel because we need to store the MAC address and that all those networking interface information in the kernel's eBPF map. So that is about 500 ms, less than that. And the map occupancy sits at less than 2% with max capacity of 1 million. Means like, and this is, by the way, per pod, means we have per pod maximum limit of 1 million, and that we can do because it's like chump change at the eBPF layer. So this is the summary, where before and after we compare like traffic capture, proxy model, data structures, rollback, app changes, and kernel requirements. There is clear improvement in every single of these areas. The ON evaluation is now constant time, no sidecar, like per pod proxy to shared proxy on every single node. Linear chain walk, hash maps, pod restart and reconcile do not needs to be done. You can do it within the pod's life cycle, because the attachment and detachment is atomic. Sidecar injection is now none. And Linux kernel requirement, although there is a kernel requirement of 5.7 plus for running this system, typically now every Linux, now the standard has been like Linux kernel 6.4, you will find everywhere. So this is nothing to be worried about. Key takeaways, 5 mental models that you can apply on Monday. First, that kernel is a deployment target. You can run your custom programs with eBPF. That in itself is a big sort of enablement in terms of running your logic at the lowest level as possible, with leveraging the actual performance of your machine. And then because there are multiple hook points, you need to plan for each hook point. Whether should I put it here, here, or here, because that could have a significant impact on how you want to do the manipulation or what kind of, whatever job you want to do. The cheapest proxy is the one that is not there. No proxy, no hop means you basically save latency, you save CPU cores, memory, and audit your data structures. Linear walks at scale could be a problem that you might not notice at lower scales, but every time you think of building a data structure, you need to make sure you can know how good optimization that you can do, because that will impact your systems at scale. Then if you can't observe it, do not run it in production. We built the dashboards at day one We built, we did not want to compromise on alerting. We did not want to compromise because these are like everything is critical in production. So these are some of the metrics that we observed, and yeah. Then migration is a posture. It's not a one-time event. Per namespace opt-in or per annotation-based opt-in for services is important. And you need to plan for breaking things in production. If things break, then you need to be quickly reverting it. Uh, yeah, that's all. There were plethora of other optimization that actually went in to put this into production, but for the sake of the talk, we can discuss it offline. And let's